Let us now solve some questions on photoelectric effect. Coming to the first one, the threshold frequency, I mean nu naught, for a metal is 7 into 10 power 14 per second. Calculate the kinetic energy of an electron emitted when radiation of frequency one point 0 into 10 power 15 per second hits the metal. Okay, so it's very simple. They have given the threshold frequency and of course asking to find the kinetic energy of electron. And they have also given the frequency of incident radiation, nothing but nu, right? So nu and nu naught are given and they are asking you kinetic energy. We know that E is equal to W plus K according to photoelectric effect. E can be written as a H nu, W, which is nothing but threshold energy or work function, can be given as H nu naught. Then keep kinetic energy as it is. Now they are asking you to find kinetic energy that can be written as H nu minus H nu naught. Now taking this here, let us take H as a common, then this will become nu minus a nu naught, right? Let us calculate this 6.625 into 10 power minus 34 joule second. How about nu? Nu is say 10 power 15. Okay. Or if you want, you can write it as 1.0 into 10 power 15. So that, this, I would actually like to write it as 0.7 into 10 power 15. Is that okay? Because when you remove this point, it will be 7 by 10. When that 10 goes into numerator, that will be 10 power 15 into 10 power minus 1. Nothing but here 7 into 10 power 14 will get. You will get that. But see, for simplification, if both are in 10 power 15 terms, it will be easy, right? Come on. This is 6.625 into 10 power minus 34. Now here you got 1 and here it is 0.7. Can I write that as 1 minus 0.7 is 0.3 and you just keep 10 power 15 as it is. So that is very interesting. Now multiply this by 3. 3 5 So this comes out to be 19.875. Of course, that is multiplied by 3. So this point has to be removed. Then that will be 3 into 10 power 14. So then this comes out to be minus 34 and this is 10 power 14. Minus 34 and plus 14. That will be minus 20. Okay. These many joules. So simplification, you can check again later in leisure. Okay, it's a very simple model to start with. I've given all the relations yesterday. E is equal to W plus KE, and we know that E is equal to H nu. W is H nu naught. Even this KE can be modified, but here it is not necessary. Okay, so that's it. Okay, let us go for the next one. This is a very interesting one, a previous IIT question, integer type question. See, the work function of some metal is given below. The number of metals which will show photoelectric effect when light off (300 nanometer wavelength falls on the metal. So they have given a list of things, metal and the work function or threshold energy. This is given in electron volts. Let me give you the list of things. Lithium, sodium, potassium, magnesium, copper, silver, iron, platinum, then tungsten. 2.4, 2.3, 2.2, 3.7. Then, of course, 4.8 for copper, then 4.3 for silver, 4.7 for iron, platinum is 6.3, and this one is 4.75. Okay. Now, the point is, this is a wavelength of the incident radiation, nothing but lambda. They have given work function or threshold energy. We know that photoelectric effect is observed only when, considering this equation, energy incident upon must be equal to W or greater than W. Isn't it? Only under these conditions, photoelectric effect is observed. If suppose you go for E is less than W, then because energy that you have given is less than the minimum required, then there won't be any photoelectric effect. Right? Now in the first case, when E is equal to W, kinetic energy of the ejected electron is going to be 0. And in this case, it will be more than 0. That means the electrons ejected will have some kinetic energy so that they can move on. Now remember, they are asking you to find the number of metals which will show photoelectric effect. I mean, we have to check for this. I mean, their work function must be either equal to the energy corresponding to this wavelength, or if the work function is less than the energy that is corresponding to this wavelength. So remember, photoelectric effect is observed only when work function is equal to the energy of the radiation, or when work function is less than the energy of the radiation that is incident upon. Now let us check the energy corresponding to this particular radiation, because anyway we have got work function. Come on, energy can be calculated in electron volts, taking the formula 12,400 by wavelength in angstroms. Can I just go for 3000 nanometers? Because, sorry, 300 nanometers can be given as 3000 angstroms. Told you already that 1 nanometer is equal to 10 angstroms, isn't it? Now, the simplification is very easy. Come on, let us just divide it by 3. 3 4s are 12, then 3 1s are 3. You are left with 1. So 4, 1, 3. I mean, it is actually 41.3 when you divide 124 by 3, but there is 30, not 3. So let me write it as 4.13. This will be in electron volts, because as per the rule, this must be in electron volts and this must be in angstrom. Okay. So now when you got the energy of the incident radiation, come on, check out the metals that fall under this condition. Work function is either equal or less. See, here the work function is less, 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 less. Isn't it? In this case, it is more, 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 more. So therefore, what are the metals that can show? Only 4 metals can show photoelectric effect. What are they? Lithium, sodium, potassium, and then magnesium, because their work function is either less or equal. Of course, they are less when compared to the energy of the incident radiation. So this is a very interesting question. It was asked in previous IIT exam under integer type question. Okay. Now, let us take another question. This is also very interesting. When a certain metal was irradiated, I mean hit, when certain metal was irradiated with light of a frequency 1.6 into 10 power 16 hertz. The photoelectrons emitted had twice the kinetic energy compared to the photoelectrons emitted. When frequency was 10 power 16 hertz. Threshold frequency is x into 10 power 15 hertz. Find the x. Even this also is a kind of integer type. But this is interesting. There are two different cases. Of course, threshold frequency or nu naught will remain constant for a metal. But in the first case, they have irradiated or they have actually hit the metal with a light of frequency 1.6 into 10 power 16. Whereas in the other case, I mean in the second case, it was hit by a radiation of frequency 10 power 16 hertz. But remember, in the first case, the photoelectrons emitted had twice the kinetic energy as compared to the second case. Let us take all those things into consideration and let us again go back to the same old relation. E is equal to W plus Ke, right? E is H nu, W is H nu naught. Keep kinetic energy as it is. But now let us write expression for kinetic energy. Come on, this whole thing will come here, right? Then H nu minus H nu naught. Come on, let us consider it this way. Taking H as common, nu minus nu naught. Right? Now let us take it this way. Kinetic energy in the first case by kinetic energy in the second case can be written as the same thing. I'm taking it for twice. H of nu1 minus nu naught, H of nu2 minus nu naught. Is that okay? Now just simple. Ke1, I've just taken this as 1 because I told you that nu naught is constant. And in the second case, I have taken nu as a nu2 because it is the second case. As usual, nu naught is constant. Okay. So now let us substitute the things. What is the kinetic energy in the first case? It is clearly mentioned that the kinetic energy in the first case is 2 times of the second case, right? That means if the kinetic energy of the second case is 1, then the first case would be double to that. Nothing but 1. Sorry, 2. Double to 1 is 2. Then, of course, this H and H get cancelled, right? How about the new one? New one is the first case. It is this. Minus nu naught. Nu naught is, of course, this. Okay. So let us find the nu naught. Of course, after finding, we can write the value of x. Right. Then in the second case, it is this minus nu naught. Okay. So let us Just simplify this as, you just cross multiply the things. Okay. So 2 of 10 power 16 minus a nu naught. Or if you want, I'll write it clearly. 1 into 10 power 16 minus a nu naught is equal to, on to the other hand, we have this, right? Come on, simplify this. It is like 2 into 10 power 16 minus a 2 nu naught is equal to 1.6 into 10 power 16 minus nu naught. Very simple now. You just take it here. This will become plus. So that becomes 2 nu naught minus this nu naught. Nothing but nu naught. Okay. Then take it on to this side. That will become minus. Hope you all know that. Then nu naught will become equal to, when you take it onto this side, it will be 2 minus 1.6. Nothing but 0.4 into 10 power 16. Or you can write it as 4 into 10 power 15 hertz. Because 0.4 can be written as 4 by 10. When that 10 goes into numerator, it becomes 10 power minus 1. So 10 power plus 16 into 10 power minus 1 is 10 power 15. So from that, we can give the final answer, x as equal to what? 4. So it's very interesting. But if you are perfect with the theory part, I think you can solve it easily. Okay. Next. Let me take one more question. Threshold frequency of a metal is F naught. Okay, I've just given it as F naught only to have some differentiation. It's of course a nu naught only, but in the problem they have given it as, when light of a frequency nu is equal to 2F naught is incident on the metal plate. Velocity of electron emitted is a V1. Now we are going for velocity thing in this particular problem. So this is in the first case. When light of a frequency, now go for the second case. When light of a frequency 5f0 is used, velocity of electron emitted, or let me say ejected, is V2. V1 is to V2 is. They're asking the ratio. Just like in the previous question, it was KE1 is to KE2. Now here it is V1 is to V2. Again, they have actually given that the threshold frequency is F0. In the first case, the frequency used was 2f0, and in the second case, the frequency used was 5f0. In the first case, the velocity of electrons ejected was V1, and in the second case, it was V2. Now they are asking you the ratio of V1 and V2. Let us just go with the same relation. E is equal to, but now kinetic energy is equal to half mv square needs to be taken. Come on, this is equal to h nu is equal to h nu naught, right? Then kinetic energy, we know that it is half mv square. Okay, now let us write it as half mv square is equal to h nu minus h nu naught, isn't it? Then h of nu minus nu naught. Everything in a crystal clear manner. Come on, let us write v square is equal to. Keeping this v square here itself, let me take the other things. On to the other hand, I think this is clear. This 2 has come here and m has come into the denominator. Got it? Now, anyway, you know, h being a constant, we don't consider. 2 is a constant. Even m is also a constant. Isn't it? So now, let us take v as equal to root over this. Nothing but root over nu naught, sorry, root over nu minus nu naught. Now taking this in 2 different cases, can I write it as root over? In the first case, it is a nu 1. In the second case, it is nu 2. You got everything. You can find out the ratio of V1 to V2. What is the frequency in the first case? 2f0 minus threshold frequency is f0. In the second case, it is a 5f0 and minus the threshold frequency is f0. The second case, the frequency is 5f0, right? So now V1 by V2 can be written as, come on, root over, the numerator is f0 and the denominator is 4f0. Cancel out these 2. Now that is equal to root over 1 by 4. Can I write it as 1 by 2? Therefore, V1 is to V2 can be written as 1 is to 2. That's it. Check out. Okay. Next. This is again a different variety, somewhat graphical. The ratio of a slope of Kmax, nothing but maximum kinetic energy. You can also write it as Ke max versus nu. And nu naught versus V. Curves in the photoelectric effect. Gives. This is an interesting question. You have to actually write the ratio of the slope. Let me tell you that we are considering the graphs between kinetic energy versus nu. And then the other one is a nu naught, sorry, V naught. This is V naught. V naught versus, let me write it as V naught. V naught is stopping potential. V naught versus V naught versus this is of course H nu is H nu naught plus EV naught, right? V naught is equal to nu minus nu naught. Because in the problem, nu and V are given like the same way. Okay, we'll take this as nu. There is some confusion in the way it is given. In the second case, of course, it is okay. Come on. Yeah, now it is clear. The first one is maximum kinetic energy versus a nu graph. Then this is V naught versus a nu. Let me first tell you what V naught is. Come on. You know, E is equal to W plus kinetic energy, right? First, let us consider this. After that, we'll go for the second one, taking the same relation into consideration. Come on, E is equal to H nu. That is equal to H nu naught plus Ke, right? Now, Ke or Ke max can be given as H nu minus H nu naught. Okay. See, from this, let me just tell you that this is similar to, now they are drawing a graph between, say this is on y-axis and this is taken on x-axis. So this, let me write it as y is equal to mx plus c. You know, when you take something on y-axis, I mean, this is your y-axis and this is your x-axis, right? You will get either a positive slope of this type. Okay, this is called slope. And this is called y-intercept. Of course, you come across this in mathematics. Now, otherwise, sometimes it may be even this also. This is positive slope, right? If suppose it is this, if this is taken as this, then this is said to be negative slope. Here, it is again y and this is x. And now this is your y-intercept. Nothing but C. C is called y-intercept. Look at this. Okay. So, come on. Now they have plotted a graph between kinetic energy, taking it on y-axis, and the nu taking it on x-axis. So, let us check. See, this is y. Now, this is your x. So, this is your slope. And this, of course, is intercept. Okay. So, what is the slope here? Slope, in this case, nothing but m is equal to h, right? Now, go for the other case, where this V naught, otherwise known as a stopping potential. Let me tell you what stopping potential is here itself. I told you that when light of a suitable frequency falls on metals, electrons are ejected from the surfaces of metal, right? This can be stopped by applying some potential called a stopping potential. In order to stop the ejection of electrons, what is the minimum potential? I mean, what is the minimum current? You can say in normal terms if you want to understand it easily. So, to stop that, what is the potential to be applied? What has to be done to stop the ejection of electrons is what I call stopping potential. Now, that can be simply given in this format. Come on. E is equal to W plus Ke. Now, E is H nu. W is, of course, H nu naught. Ke can be written as E into V naught. Look at this. Kinetic energy is equal to, it is nothing but charge. And this, of course, is potential. In fact, kinetic energy can be given as charge into potential. You must be knowing this if you have come across this in physics. But here, because it is not just V, it is V naught, I call it stopping potential. Okay. All right. Now, come on. Let us again go back to our y is equal to mx plus c kind of thing. So here, let us take it this way. EV naught is equal to h of nu minus nu naught. Right. But they are plotting a graph between just V naught and nu. So even this E has to be taken on to the other hand. So let me write it as h nu by E minus h nu naught by E. Okay, na? Then, come on. This is right, like your y is equal to mx plus c again. Now, look at what is y and what is x. This is y. Yes, clearly mentioned. This is your y. And this, of course, is x. Come on. Y is equal to, this is your x. The remaining thing is, m, nothing but your slope. Now, this is, of course, intercept. So, what do you write? Slope in this case is equal to m, and that can be given as h by e. Now, finally, they are asking the ratio of slopes in the two cases. This is, of course, case 1, and this, of course, is case 2. Right? So, slope in the first case, let us write this as slope in the second case. Slope 1 by slope 2. This can be written as h by e. H and h get cancelled, and this e goes into numerator. So the final answer is E, nothing but charge on electron. So this is the final answer. Check this out. This is very interesting. Unfortunately, we could actually come across this slope and intercept thing also. You must be knowing this if you have come across this in physics, or if suppose you were taught this in mathematics. But otherwise, you just check out the things carefully. You need to know what is y and what is x. Hope that is clear. Next. Now, let us take one more question. Again, an interesting one. Photoelectric emission is observed from a surface for frequencies nu1 and nu2. Nu1 and nu2. The kinetic energy in the two cases are in the ratio one is to k. Then the threshold frequency nu naught can be given by. Okay. So, of course, I think you can solve this question because it's again on the basis of the relation between kinetic energy and the frequencies. Of course, the threshold frequency also is taken into consideration. But there is some interesting point. Remember here it is nu1, of course. It is also given that nu1 is greater than nu2. Let's see how to solve this. Same old. E is equal to W plus K. H nu is equal to H nu naught plus K. Now let us write expression for K. H nu minus H nu naught. Okay. Kinetic energy in the first case. Okay, let me write one more step. After that, we'll go for two different cases. Even this also is written many a time. Kinetic energy in the first case by kinetic energy in the second case. I'm sorry, here it has to be just new. But now I can take it as nu1 because I have taken it for the first. Then in the second case, it can be written as nu2 minus nu naught. So, okay, just cancel out h. See, ke1 is to ke2 can of course be written as 1 by k. Isn't it? It is clearly mentioned here. In the first case it is 1. In the second case, it is 2. Come on. What is nu1? Yeah, you can just take it nu1 only. Then, of course, nu naught by nu2 minus nu naught as usual, as it is. Come on, let us cross multiply the things. Yes, it can be written as k of nu1 minus nu naught, nothing but k nu1 minus k nu naught, isn't it? Because this k multiplies for both. Then take nu naught minus nu2 minus nu naught. And look at this now. Because nu1 is greater than nu2, let me take this nu2 onto this side. If it were to be nu2 is greater than nu1, then we would have taken this onto this side. Hope you got my point. Now let us write this as k nu1 minus nu2. Otherwise, it would have been nu2 minus k nu1. If it were to be nu2 is greater than nu1. But here, because they have given that it is nu1 is greater than nu2, let me write it this way. Now this nu2 has come here. Let us take this onto this side. Come on, that will become positive. K nu naught minus nu naught. Right? So, what is this? Let me write this as nu naught is taken as common. Then it becomes k minus 1. Is that okay? Come on, let us write. Okay, let me write even this also for clarity's sake. Now I'll be writing the final expression for this nu naught. Come on. Nu naught can be written as k into nu1 minus nu2 by k minus 1. That's super. Check this out. Okay. Next. Now let us go for one more interesting problem. See, a light source of wavelength lambda illuminates a metal and ejects photoelectrons with a Ke max equal to 1 electron volt. Another light source of wavelength lambda by 3 ejects photoelectrons from the same metal with a maximum kinetic energy equal to 4 electron volt. Find the value of work function. Very interesting. Now here it is the relation between kinetic energy and wavelength. This is the first case. Coming to the second case, kinetic energy and the wavelength. Finally, they are asking you W. Let's see. It is actually E is equal to W plus KE, right? Now, this is the wavelength of the incident radiation. Come on, let us take this E as a hc by lambda and keep W and KE as it is. Because you got lambda given in the problem. Of course, there is kinetic energy. And of course, they're asking work function. Come on. Let us write this as KE is equal to hc by lambda minus W. Okay. Now this has to be given for two cases. In the first case, kinetic energy is 1 electron volt. That is equal to hc by lambda as it is minus W. Okay. Now in the second case, this is case 1 and this of course is case 2. 4 electron volts is equal to hc, but now the wavelength is lambda by 3 minus W. Work function of course is same. Okay. Now solving the two equations, 1 and 2 will give you the final answer. This can of course be written as, let us do one thing. Let us write this as solving the 1 and 2. Will actually give us the answer as W is equal to 0.5 electron volt. Okay, this needs to be solved. We'll check that out.